Hello everyone, welcome back to my channel. Today's topic is Martingale theory first episode. And in this first episode, we're going to talk about conditional expectation. We're going to define what is a conditional expectation. And then we're going to we're going to see why conditional expectation exists. So first, we know conditional expectation in elementary probability theory is given some random variable. You know something, and then you try to find the conditional density function, and then try to find the conditional expectation of some random variable. But what is a conditional expectation? Why we can do that? This in the elementary probability theories, those were not talked about. It's just being given that you can find the conditional expectation by finding the conditional density function and then calculate that using integral. So there's no reasoning being taught why is the case. And today we're gonna start talking about Martingale. It's talking about the conditional expectation. We're gonna start the foundational theory of the whole things we've seen in the elementary probability theory. So first, let's talk about what is a conditional expectation. So given a probability space omega f naught, let's say, and probability measure p, and also given a space f, which is a subspace of a subsigma field of f naught, and the random variable x, given the random variable x has a finite expectation, then the conditional expectation for x, given the smaller sigma field f, which is telling us that okay, we know something, we don't know anything, we don't know everything, but we know something. So there's something we know is now the whole sigma field f naught. It's a smaller sigma field inside this bigger sigma field. For example, we know something that the x is less than a certain constant. We know the probability for that. Then we also know the inverse. So when the x is greater than the constant c, then so we know this is the simplest sigma field. We're gonna talk about later as well. So we know something. It's tiny information of a bigger sigma field. What is we want to find a conditional expectation of what we know, and we want to find the expected value of x given what we know. So that's conditional expectation. So what is that? By the formal definition of conditional expectation, conditional expectation is a random variable. It's a collection of random variables. Any version of that conditional expectation satisfies, by definition, we'll define that this, and we're gonna see how that will match what we see in the elementary probability theory. So the conditional expectation is a random variable that is any random variable y that satisfies these two conditions. First, this conditional random variable y is a projection of x onto the sigma field f, the smallest sigma field f, which means that the conditional expectation is f measurable. Second, for any event in this smaller sigma field f, the integral of x on this event any event e, equals to the integral of the conditional expectation random variable y, which is a version of the conditional expectation. They are equal on any event e in f. So that's the definition of conditional expectation. So I just mention just a little bit that this random variable y is a projection of x onto the space of f. So we want to find the conditional expectation is a random variable in this functional space of it's a Hilbert space, that this y is the closest to x in this measurable space f. So you can think about that it's a triangle. This x was being projected onto a Hilbert space of f, measurable functions of f, and that is the closest measure of to x. And there could be many y's. So if we have two versions of y, that's y and y prime, we can see, we will see later, these two y and y prime, they actually equal almost surely. So that's the conditional expectation. Let's look a little bit more on this equation here. So why this is being used as definition of conditional expectation? So we want to find expected value of x, and that is a measure on what we have known so far, which is the sigma field f. Then the best estimate of x is a random variable y that is measurable with respect to f, and they are basically almost surely equal, or of x and y on the space f. So we want to estimate x as long as our estimation y is very close to the x on the space of f, right? So that's very it's very intuitive way of understanding why this is being used as a conditional expectation of x. So the next thing is just mentioned is if y prime is another version of that conditional expectation, then they are almost surely equal. And it's very easy to prove that. We can first look at the set of y is greater than y prime, and if that y minus y prime is greater than some positive epsilon, then this set A, we want to prove that this set A has probability measure 0. And it's actually true because by the definition of conditional expectation, it's actually equal to integral of x minus x is equal to integral of y minus y prime. So that integral is equal to this one. This integral is equal to this one. So these two are equal, and this is just 0. So and this is just by the definition is greater than or equal to epsilon times probability of p p over a. And for this to be less than or equal to 0, epsilon is positive. The only thing we have is probability of a is 0. And conversely, we can see that the other direction, when y prime greater than y, this set it also has more probability measure 0. So that's very easy to see. So the next thing is that we want to see is we define this one, right? We define a conditional expectation very intuitively. This is how we define conditional expectation. But why this conditional expectation exists? How do we know that there always exists a y, right? We don't know that we can always find a y that is close enough to x given the random given the sigma field f. So the existence of y must be proved, and that was proved by the Radon-Nikodym Theorem. It's one of the most important theorems in in mathematical analytics and in probability measures. A very, very important one. And before we talk about that, I mention about this theorem, I want to mention that in the elementary probability theory, we also mentioned we also told, okay, a probability distribution, there's always a probability density function. And from now, you have to understand that it's not always true. Given a probability distribution, you may now have a probability density function. And the condition for the existence of probability density function, and also the existence of conditional expectation, is guaranteed by the Radon-Nikodym Theorem. If the conditions, the assumptions are satisfied for what is given in the Radon-Nikodym Theorem, then we can say that this certain any given the given probability measure has a density function or has a conditional expectation. So let's look at what is the Radon-Nikodym Theorem. So given mu and nu are sigma finite measures. So what is sigma finite measure? I didn't write it down here. Forgot to write it down. But sigma finite is for a space omega, if we can find if there's a increasing set of AI that will increase to omega from A1, A2, and so on, and the measure of each AI are finite, then the measure is sigma finite. So basically means that we can cover the whole space by finite measure sets, and those finite measure sets increasing finite sets. Each of the set AI has a finite measure. And an alternative way of defining sigma finite is that we can separate this increasing subset AIs into disjoint sets, finite sets. So we can basically reorganize those increasing subsets into disjoint subsets, and they are finite. So they are basically the two same definition. And also, mu is absolute continuous with respect to nu is absolute continuous with respect to mu. What continuous absolute continuous with respect means is that if mu is for given set A, if mu A is 0, then nu A is also 0. So whenever a set that has measure 0 with respect to mu, that set A also must have measure 0 with respect to nu. And if that condition is satisfied, then nu is absolute continuous with respect to mu. So that's the definition of that. You can think of that if the back measure on a set has probability measure 0, then the corresponding probability measure nu also have probability measure 0 with respect to the same set. So given that mu and nu are sigma finite measures on this space, and nu is absolute continuous with respect to mu, then there exists a f measurable function f such that for all a in this sigma field f, the integral of f d mu is equal to nu a. So and f is usually denoted by d nu d mu, like what we see in fundamental calculus, and that function f is called the Radon-Nikodym Theorem, Radon-Nikodym derivative. We won't be proving that here. We're gonna look at the results of the Radon-Nikodym Theorem here. So the first thing is the existence of probability density function. For any let's define we can let mu to be the Lebesgue measure, which will be pretty much the same as what we see in Riemann derivative, right? dx. Then any probability measure nu that is absolute continuous with respect to mu, then nu has a probability density function, which is the Radon-Nikodym derivative f. So if any probability measure they are absolute continuous with respect to Lebesgue measure, then we can say this probability measure definitely have a probability density function. So that's the condition of guaranteeing the existence of density function. The next one is existence of conditional expectation. That we haven't proved. So we want to prove this is what we want to prove here. How do we know that the conditional expectation random variable y exists? There is such thing. How do we know? So, and that is also proved by Radon-Nikodym Theorem. So the proof is very easy as well. We can first assume that the random variable x is positive, and we can also let mu in the Radon-Nikodym derivative, let mu to be the probability measure p we have in here, and then we define the new measure measure on A to be the integral of x on the set A, and for all A in the sigma field F. Then nu is a measure. It's very easy to prove it is a measure. You use disjoint sets of AI, and it's a disjoint added of nu AI, summation of all H AI, and nu is absolute continuous to mu, because if probability p on the set A is probability measure 0, then the whole integral is definitely have a 0. So this two condition is satisfied, then we can use the Radon-Nikodym theorem. So this nu A must have a Radon-Nikodym derivative, which is d nu d mu, and integral of dp, and dp is just d mu, right? So that guarantees the existence of a version of our conditional expectation. For any x, that's also easy. We just have to separate the x to be a positive part and negative part, and then use the same condition use the same Radon-Nikodym theorem, and that prove the existence of any random variable x of the existence of the conditional expectation. And that's it, everyone. I hope you like it, and bye.